So what if your computer didn't just spit out an answer, but could actually give you a mathematical proof that the answer is correct? I mean, completely, undeniably correct. Well, that's the core idea behind a huge new initiative called Project Nexus, and it's aiming to do nothing less than change the very foundation of how we compute. And this right here is the question at the heart of it all. It's not just about making one computer verifiable. No, the goal is way bigger. To create a global network where pretty much all of humanity's computation can be collectively proven. It's a seriously bold vision, right? Okay, so what does verifiable computation actually mean in practice? Let's break it down. Think about your calculator. You type in 2 plus 2, and it tells you 4. You just trust it. With verifiable computation, it would not only show you 4, but it would also hand you a kind of cryptographic receipt that mathematically proves the answer couldn't have possibly been anything else. It's a guarantee, without you ever having to see the secret stuff happening inside. You know, this is a much bigger deal than it sounds. Since the very beginning, since the days of Turing and von Neumann, our entire digital world has been built on a foundation of trust. We trust the hardware, we trust the operating system, we trust the apps. Project Nexus is proposing a completely new game, one based on mathematical certainty instead of just blind faith. Now, you're probably thinking what I'm thinking. If this is so amazing, why don't we have this everywhere already, right? If verifiable computation is this powerful, what's been stopping it from being a part of our everyday lives? And that gets us to the absolute core of the problem that the Nexus paper is trying to solve. Turns out, generating these mathematical proofs has always been incredibly, brutally hard and inefficient. It's forced developers into a corner, making them choose between some really painful options. And here's that dilemma. On one hand, you've got what they call the ASIC approach. Think of it like building a custom-designed train that only runs on one track to one destination. It's ridiculously fast for that one job, but it's totally rigid and you need a team of geniuses to even build the track. On the other hand, you have the CPU approach. This is like a car. It's super flexible, can go anywhere, but for really complex jobs, it gets stuck in traffic and becomes astronomically slow and inefficient. So developers had to pick raw speed or go anywhere flexibility. You just couldn't have both. And for developers trying to build things with this technology, it was a total nightmare. These systems had huge performance problems, they were basically useless for any kind of long-running program, and their complexity made them a minefield of potential security bugs. All these issues together built a giant wall, keeping verifiable computations stuck in the lab. All right, so this is where Project Nexus rolls in. It's a brand new architecture designed completely from scratch to just demolish that dilemma and finally make verifiable computation practical for the real world. The whole system is built on 3 key parts. The best way to think about it is like a super high-performance race car. First, you have the Nexus zkVM. That's your universal engine, the powerhouse that can prove any program you throw at it. That engine runs on the Nexus Virtual Machine, the NVM, which is like a custom-built, perfectly smooth racetrack, designed for one thing and one thing only, pure, unadulterated speed. And then you have the secret sauce, zkVM coprocessors. These are like specialized turbochargers you can bolt onto the engine for a massive speed boost on specific, heavy jobs. These coprocessors are the real game changer here. They're what finally solves that old speed versus flexibility problem. They let developers plug in these custom, hyper-optimized instructions right into the virtual machine. So for instance, proving something common like a SHA-255 hash is normally painfully slow. But with a dedicated coprocessor, it's like dropping in a specialized piece of hardware. It makes the task up to 1,000 times more efficient without ever sacrificing the flexibility of the main system. It's the best of both worlds. So how does this whole thing work in practice? Well, first, a program gets compiled for the Nexus Virtual Machine. As it runs, it creates this super detailed log of every single step it took. That's called an execution trace. Then the magic happens. It's a step called folding. The system takes that long trace, breaks it into millions of tiny little pieces, and generates proofs for all of them at the exact same time in parallel. Imagine a million people all working on tiny sections of a giant jigsaw puzzle at once. And finally, all those little proven pieces are folded and compressed down into one single tiny package using a technology called a snark that verifies the entire original computation from start to finish. Okay, but even with all these amazing optimizations, generating proofs for really, really big computations needs a mind-boggling amount of processing power. And that's where the second huge piece of this project comes into play, the Nexus Network. To get to that massive scale, the project borrows an idea that you might actually be familiar with. You remember projects like SETI at home, where people donated their computer's idle time to help search for alien signals? Well, the Nexus Network applies that exact same idea of large-scale distributed computing, but directs it at generating these zero-knowledge proofs. So yeah, what it is a distributed network designed to pool together computing power from all over the world. We're talking everything from a phone to a giant data center full of GPUs. And all that power gets channeled into that parallel folding step we just talked about. This network is what allows the whole system to scale up to global size. And here is the absolutely critical difference from something like SETI at home. In those older projects, you kind of just had to hope the results from volunteers were correct. But in the Nexus network, because the output of every tiny little task is itself a proof, the entire system is verifiable from the ground up. You don't have to trust anyone. The math itself guarantees that the final result is legit. And the scale we're talking about here is just staggering. The goal isn't just to prove a few small programs. The goal is to build a system that can prove trillions of CPU cycles per second. That's a level of verifiable computation that is just worlds beyond anything that's even remotely possible today. So let's zoom out from the tech for a minute and look at the really big picture. What's the ultimate vision? I mean, what kind of future does this technology actually make possible? This quote from the paper's abstract, it just nails it. This is about completely re-architecting our digital world. It's about building a future where we don't have to blindly trust the platforms and services that we depend on every single day. Seriously, think about what this means. This could change how we vote, how our financial systems work, how scientists verify their research, everything. It's about ripping out these opaque, trust-based systems and replacing them with transparent, verifiable ones. It's a fundamental move from a world of trust me to a world of show me the proof. And that really leaves us with this final, powerful question. Once this kind of verifiable computation becomes cheap, scalable, and easy for any developer to use, what new things become possible? What amazing systems that seem like science fiction today become totally doable tomorrow when you can build them on a foundation of pure mathematical truth? It's a pretty exciting thing to think about.